Hello, this is Dr. Michael Hassan, the engineering doctor, and this is lecture number 28, VHDL Design 4 of Chapter 5, Arithmetic Network Design of the course Digital Logic Design, Digital Systems or Digital Electronics. The next slide is a disclaimer for you to read. The next slide is a list of references. I listed 3 references for you, but there are many references online. In Chapter 5, we talked about the design of binary adders, design of binary subtractors, design of magnitude comparators, design of binary multipliers, design of ALUs, and we'll conclude with VHDL design. In the design of half-adder, we will define the half-adder simply by 2 inputs, 2 A and B, each consist of 1 bit, so they are the N in standard logic, and S and C out are the out bits in standard logic. I will end the entity name half-adder. Architectural logic functions of half-adder begin. I have 2 signals to assign, A exclusive or B to be assigned to S, which is the sum. This came from the definition from the truth table of the half-adder. And C out will be assigned with A and B. I will end the logic function. Compile and simulate or download on a chip and test it. And I have the full code for half-adder. The next code is for full-adder. The same thing, the entity will be defined as full-adder, the entity name. The port is C, N, A, and B. Those are in. And S and C out, they will be the out. I have the sum and the C out. The architectural logic function of full-adder is will begin. I have A exclusive or B exclusive or Cn will be assigned to S. To the sum, this came from the truth table. And A and B or Cn and A or Cn and B will be assigned to C out. I will end the logic function. Now, if I would like to use the full-adder to a larger size adder, I have 2 approaches. Either I can declare the full-adder as component within the code, the higher size, the larger size code, or I can package the full-adder, declare it as a package, and I can call it anytime in any program. This is a better approach, will be a more general approach, and make the life much easier for you if you'd like to use the full-adder in many other programs. Okay, so to do that, we'll come to the example where I would like to design a full carry ripple adder. The carry ripple adder will have Cn, will have a 4-bit input numbers, A3, A2, A1, A0, and B3, B2, B1, B0. We'll have 4-bit sum, S3, S2, S1, and 0 will be out, and C out, which is the final carry out, will be an out, okay, in standard logic. I will end the entity name 4. Architecture structure of adder 4 is, I will declare a signal. Those are the internal carry out. The first stage, stage 0, full adder will have a carry out C1. Stage 2 will have a carry out C2. Stage 3 will have a carry out C3. And stage number 4, the final stage, the carry out is the carry out of the 4-bit carry ripple adder. So this is the final carry out. So we don't care about it. So we have 3 signals to declare C1, C2, C3. Now, I declare the full adder as a component, and I will add component. When I define it as a component, the port definition of this component has to be identical to the entity full adder when we declared it as entity full adder in another program. Once I declare it as component, I will end component. Once actually I declare it as component, I can use it in a port map statement. So I will say full adder, FA0, full adder port map. I have Cn, this is the original carry in coming to the first stage, to stage 0. A0 and B0, I'm adding A0 and B0 and Cn. The output sum is S0 and the carry out C1. Not carry out is C1. This is internal signal, which is the carry out of stage 0 to be taken to the next stage. C, those has to be at the same level. I have Cn, the A, the B, the sum, and the carry out has to be in sequence. The same sequence is defined in the component the same sequence defined in the entity. So the next stage I will have C1, A1, B1, and the next bit, S1, the sum, and C2, which is the signal, the internal signal will carry out of stage 1, of the next stage of full adder 1. Now C2, A2, B2, and the output S2 and C3. C3, A3, B3, and the output is S3 and C out. So my output will be S0, S1, S2, S3, and C out. I will end the structure and I finish the program. If I don't want to declare it as component in the program, I will package it. I will write a package declaration for the adder. This declaration could be placed after the entity full adder and they can be compiled together, or could be written separately as a program and compiled separately. So it is your choice. Library IEEE standard logic 1164.L. The package full adder underscore package is component full adder. Again, those are that came from entity name. Standard logic in component in full adder package. Compile it, super easy. I can use it. I can call it anytime through the work statement, the work library. So I will say library IEEE, use IEEE standard logic 1164.all, use work.fulladder underscore package dot all. Entity adder 4 is port. I will have CN. A3, this is the same definition that we used. 4-bit A number, 4-bit B number, and 4-bit sum out and carry out from the 4-bit carry ripple adder. I will end 4. Architecture structure of adder 4 is, I will declare the signal C1, C2, C3 because those are the internal signal, the internal carry out. C1 from stage 0, C2 is the carry out from stage 1, C3 is the carry out from. We don't need C4 because C4 is C out. Okay, it's already declared as output. Okay. So begin. F80 will be the full adder. This is the port max statement. Okay, I have Cn, the carry in, A0, B0 to be added, S0 is the sum, and carry out C1 will be the carry in for the next stage. A1, B1, S1 is the sum bit, and C2 is the next stage. Okay, C2 with A2, B2, and I have S2 and C3. C3 comes as Cn for the final full adder with A3, B3, and S3 and C out. I will end structure, and by this I have finished the program. I have finished the program, but I used the full adder package to design my 4-bit carry ripple adder. Let's talk about half-subtractor. That's super easy because very similar to half-adder. Only I have the equation has been changed. D, the difference will be A exclusive or B will be assigned to D, and not A and B will be assigned to B out. The borrow out, so I have A and B in my entity N, and D, the difference and B out are out, and this is a half-subtractor. Okay, then I will end the structure with end logic functions. So this is very simple. The full subtractor, the same thing, just the equations has been defined separately. And I will package the full subtractor after the code. See, I am showing you as an example that the packaging could be done within the entity name full subtractor. So full subtractor will be defined by borrow in A and B, and the difference D and B out. Then I will have the architecture logic function of full subtractor will begin. X exclusive or B exclusive or Bn be assigned to D, and not A and B or Bn and not A or Bn and B will be assigned to B out. I will end logic functions. I have finished the full subtractor code, VHDL 4. I can compile it, but I can add another code. I will start with library IEEE, use IEEE. I will package it as full subtractor underscore package is, declare it as component. This is a copy from here, B in A, B, D, and out at B out as out. I will end component and end full subtractor package. I will compile them together, By compiling them together, actually, I will have the Full-Subtractor been designed and has been packaged at the same time. Very easy approach. Also, I can use a 4-bit carry ripple subtractor using a Full-Subtractor package. I will use work Full-Subtractor package.all. I will link it. Entity subtractor 4. I have bn borrow n. Then I have a 4-bit A number, 4-bit B number, 4-bit difference, and B out, which is the final borrow out. Okay. Then I will add the subtractor 4. Architecture, I will have internal signal C1, C2, C3 as we used it. Then we have the port map statement, Bn, A0, B0, the output D0, and C1, which is the borrow N to be used for the next one. C1, A1, B1, D1, and C2 to be used for the next one. And we have the final full subtractor. I would do it C3. You don't have to do this. C3, A3, B3, D3, and the final B out. So this could be changed. I will change it for you right here, and in structure. Okay. So the port map here will be C3. It's easier to do it like this. C3, A3, B3, and D3, and the final borrow out, B out. So the final out, B out, which is already declared in the entity. And by doing that, I do have the complete 4-bit carry ripple subtractor using full subtractor package. Okay, if you allow me to go to the next slide, this is the full subtractor. Now let's do 1-bit magnitude comparator. I have entity comparator 1, the input A, B, and I'm comparing A with B with 3 output function F1, F2, F3, F1 if it is larger than, F2 if they are equal, and F3 will be equal to 1 if A is less than B. I will add comparator 1, which is the entity name. Architectural logic function of comparator 1 is begin. Those came from the K-map from the truth table. F1 will be A and not B. F2 is A and B or not A and not B. And F3 is B and not A. So we define those equations, these logic functions. I will end logic functions, and I have a complete code for 1-bit magnitude comparator. 1-bit magnitude comparator. Let me look at 2-bit binary multiplier. This is again by using, I have A1, A0, B1, B0, and I have 4-bit product out, standard logic. Okay, in multiplier 2. And logic function of multiplier 2 is the super easy. I will have P0, P1, P2, and P3 already been defined, and we use K-map to derive those equations. And I will end logic function. I will have complete code for 2-bit binary multiplier. And finally, we'll design an ALU. This is a simple ALU, but we can have a very complicated ALU. The inputs to the ALU, we have the number A and B. And here it's a 4-bit ALU, so I have A and B, they are 4-bit, defined as standard logic vector, 3 down to 0. I have the select signal is a 3-bit because the ALU has 8 functions, okay, and 2 down to 0. And I have F out. F is a 4-bit function, has to be because it's 4-bit technology, and F will be out in standard logic vector 3 down to 0. I will end ALU4. This is a 4-bit technology, as we said. Architectural behavior of ALU is begin, process. The process, the sensitivity list of the process is S, A, and B, because those are the inputs and the signals that they change. Okay, begin. Case S is when S is 0, 0, 0, F will be all ones. You can define any functions for F. We need to define F all ones. And if S is 0, 0, 1, when S is 0, 0, 1, F will be B minus A. So B minus A will be assigned to F. A minus B will be assigned to F when 0, 1, 0, and so on and so forth. So you can have multiplication functions, you can have addition, you can have OR gate. For example, this is subtraction, A minus B, A plus B, okay? And we have exclusive OR, AND gate. And when others, I will assign F0, 0, 0. So we don't say really 1, 1, 1 because the others, this is the termination of the case statement. So when others F will be 0, 0, 0, I will end case. In the process, in behavioral, we have to end the process, the case, the process, and the behavioral, which is the architecture. And we have a complete ALU design. Super easy, very, very nice. And I would like to thank you so much. This is the end of the chapter 5 of the Digital Logic Design course. And I would like to thank you so much. We'll start with chapter 6 in the next lecture, which is lecture number 29. Please subscribe and hopefully to see you soon in the next lecture, lecture number 29. Sincerely, Dr. Hassan.